Okay, this is a continuation of the lecture on section 2.9, which is differentials and linearizations. On Tuesday before break, we introduced the linearization of a differentiable function, and today we're going to take a slightly different perspective, but do essentially the same thing. Just the philosophy is that the tangent line can be used for approximating a function. So let me start with just a diagram explaining the concept again. Imagine that we are studying a function, y equals f of x, and we know it to be differentiable at a point x equals a. And so that just means that the limit definition of f prime of a is well defined, and you get some well-defined tangent line to the curve. So let me draw a tangent here. And of course, the main idea is the same thing it was yesterday. The function is approximated at x equals a. So if f is differentiable at x equals a, then f is approximately equal to its tangent line, which we studied yesterday, let's say, which is the linearization. In other words, f of a plus f prime of ax minus a. Okay, so it's the same idea, as I said, that we're going to do today. We're just going to change up the notation slightly. So we're going to sort of switch from the perspective of trying to estimate values of f of x. So that's what this is good for. This is useful when estimating values of f of x for x near a, because it's just easier to plug a number into a line than it is to some other function, right? That's the whole purpose. Instead, today we're going to imagine that we are taking a small change in an independent variable. And of course, if y, the dependent variable, depends on x through the function, then any change in the independent variable may result in a change in the dependent variable. So if I sort of move a distance of delta x, using the symbol delta x for change in x, away from this x value a, then there's going to be a resulting change in the y coordinate. So the x coordinate of a has a corresponding y coordinate of f of a, and then if I change the x coordinate delta x units, then I could ask about, how much did the dependent variable change? So in other words, what is f of a plus delta x? What is this distance here? If this changed by delta x, how much did this change? So that distance, that amount of change sort of felt by the dependent variable resulting from a change in the independent variable is denoted delta y. So any delta x is going to result in a delta y. So let me write that down as an actual definition here. Delta y is basically how much the y variable changes when you change the x variable from a to a plus delta x. Okay, and of course the point of the section is, well, I don't want to compute that directly. Like maybe a is easy to plug into the function, but perhaps a plus delta x is a little bit awkward to plug into the function. So instead we want to use the tangent line, which I've got drawn here, to do something a little bit different. So what if I didn't want to compute f of a plus delta x? Instead, I could just sort of plug a plus delta x into the tangent line. I mean, that would be the linearization perspective. This value right here, L of x, that is approximately equal to the function value, right? This distance is small the closer you are to x equals a. Okay, so so we're not really interested in this lecture in approximating the function value there. I'm really interested in the change. So I'm going to use this distance, which presumably is easier to compute, to estimate this distance here. And this small distance in the dependent variable is called dy. Okay, so my next task is to sort of figure out what dy is. I mean, obviously from the picture, delta y, which is what I'm interested in estimating right now, is approximately equal to, oops, dy, not dx. Okay, dy. So what is dy? How do I find dy? When x is the independent variable and y is the dependent variable, we represent notationally small changes in those variables slightly differently depending on which one's the independent and which one's the dependent. So whereas the actual resulting change in the dependent variable is represented with delta y, the approximate change in the dependent variable that's estimated from its tangent line is called dy. Whereas with the independent variable x, both delta x and dx represent the change of the independent variable from the value a over to a plus delta x. So when I represent, the value or how to figure out what dy is, dx is the notation that we're going to use. So just take a look at the picture. Dy is this distance here, and dx or delta x, whatever you want to call it, is this distance here. And these two lines, this rise line and run line, are exactly the lines that you would use to compute the slope of the tangent line, right? So the rise dy, which is the unknown quantity right now, over the run quantity dx is equal to f prime at a, which is the slope of that line. Maybe I should write that down. So the slope of this thing right here, the tangent line, the slope, since it's being drawn at x equals a, the slope is f prime of a. And so these small distances that I've named dy and dx, when stacked on top of each other, give me f prime of a. Now this is a little bit perplexing because what I've written down is very familiar, right? I mean, dy dx is another name, it's another notation for the derivative of the function. And I mean, that's not an accident. I mean, this particular type of notation was built from exactly this picture. So that's why it's sort of, this analysis is reproducing something that we have already seen notationally. Well, this equation is true from the picture, and I can come back up here then and say explicitly, like, what is dy? What is the approximate change in the dependent variable when you change the independent variable by dx from x equals a? It's this right here, f prime of a times dx. Now, before this section, it sort of wouldn't have been legitimate to multiply this equation by a dx because this unit right here was, just purely a symbolic representation of the derivative. But in our picture, we are now labeling small distances with dy and dx respectively, so it makes sense to sort of multiply through this equation by dx. So this right here is called the differential, y at x equals a, and it's not really giving us anything different theoretically than what the linearization does. It just, is a quick formula for when you are trying to estimate changes in the dependent variable rather than if you're trying to estimate certain values of f of x. So let me just mention that this differential expression that I've sort of created from scratch, or from the picture, if you will, is indeed a rewriting of the linearization. It's the exact same thing written in a different way. So let me show you that by returning to this linearization expression and just observing what the quantities are in the picture. Notice that what I'm doing is when I have an x value of interest, x equals a, and I move slightly over to a new x value, a plus delta x, then that amount, the new x value minus x equals a, I'm calling dx. And if you also look in the picture, the dy expression, which I'm calling the differential, is exactly the L of x value, the linearization of the function at this new x value, minus the function evaluated at the, sort of the good x value, a. So the vertical distance dy is exactly Lx minus f of a. So if I subtract f of a from both sides, okay, and I've made the observation that this x minus a is really dx, and now further observe that this quantity right here is simply dy, then I'm getting from the linearization expression the differential expression that I have derived above. So these concepts are one and the same. The only difference is a difference in notation, and as I've said, it's a slight change in perspective. With the linearization, we're estimating function values f of x near the x value a. With differentials, we're using the differential to estimate changes in the function values relative to small changes in the independent variable. So I'm going to estimate using the differential a square root expression, and you could totally solve this problem using the linearization. In fact, it uses the exact same numbers at some point. It's just a slight change in perspective, that's all. So I want to estimate square root of 105 using differentials. Okay, if I was just like asked on the street to estimate the square root of 100.5, I'd obviously say 10-ish, which is a good estimate, right? A little bit bigger than 10. Differentials will give us another estimate, which might be a little bit closer. Of course, depending on how far you are from your sort of target square root expression, it may be less accurate, but anyway, we'll get an idea of what this does for us. So first I want to identify like what the f is, what the a is, and everything, so I can put this into the context of everything that we drew up here. So the function should be square root of x, and the a value of interest, I mean, I get to sort of choose that, and I'm just going to pick an a, just as I would with linearization, that is easy to plug into the function. Okay, and it looks like if I'm trying to get an estimate for what the square root of 100.5 is, I'm wondering how far do I need to go from 10 in order to estimate, you know, the change in the dependent variable that was felt by a change of the independent variable from 100 to 105. So the change in the independent variable is 1/2, of course, and I already know that f of a, which is 10, is, you know, is what where my dependent variable starts. I want to know then dy, that'll approximate for me how much that dependent variable has moved away from 10 when 100 moved over to 100.5. So I mean, I'm just putting like different words on top of the very same problem that we would do with linearizations. Okay, so let me crank out the derivative because that's going to be helpful for the differential formula. F prime, of course, is 1/2 x to the negative 1/2, and f prime at the number of interest is 1/2 square root of 100, so we're looking at 1/20. So dy is going to be f prime of the a value, in this case 100, I've just computed that, times dx, which is 0.5. I'll be clear about this. So this was f prime at a, and this is dx or delta x. And so what I have here is 1/20 times 1/2, it's 1/40. So I know that, you know, the differential estimate for this value is 10 plus 1 over 40. Because this is estimating how far away from f of a plus delta y actually is. I realize I've accidentally put equal signs here. This is approximately equal to. Okay, great. So there's absolutely no advantage to using differentials to do this estimate. Linearization gives you the exact same thing. I just wanted to show you the new concepts with some numbers. Okay, let's run through another example of using differentials to estimate something. And in this problem, you can really get a feel for why the perspective of change could be useful depending on your context. So let me go ahead and write out the problem. Okay, so let's read the question and see if we can understand what it's asking, and then try to fit it into this context of differentials where we're estimating the change in some dependent variable in a function. So I have to paint this hemispherical dome. That just means half of a sphere, of course. And I want the paint to sort of evenly coat the thing with a thickness of 0.05 centimeters. And the dome is pretty big. It's got a 50-meter diameter. So let me draw the picture of a hemisphere over here. Okay, a hemisphere more or less. And I want to imagine covering this thing with paint, and that's going to sort of, increase the thickness of the surface of this, and I have to sort of draw that thickness somehow. It's obviously going to be out of scale completely, but just imagine increasing the thickness of this thing by 0.05 centimeters by applying paint, all right? So I want to, and of course the question that is asking, they want to know how much paint I need, amount of paint. Like, think about how you buy paint. You buy paint in containers, right? And like when you ask for an amount of paint, think about the units on that. It's not like you're asking for centimeters of paint, or even like, typically you're not going to order the paint in terms of area either, even though like you're using paint to cover an area. Paint is a liquid and it's just fundamentally three-dimensional. So you're going to order the amount of paint as a volume. It's like how many gallons of paint you need, how many liters of paint you need. So I understand the whole amount of paint question. I need to answer it in terms of volume, and that sort of inspires me to use the volume equation for a sphere to interpret this whole thing. So if you have a sphere with radius r, then we know the volume of a full sphere to be 4/3 pi r cubed. Okay, we only have a half a sphere. Yeah, half a sphere. So this is going to be 2/3 pi r cubed. And now I can take a look at this and imagine, what differentials would have to do, or how it could help us figure out the answer to this question. When I talk about a very small change in the thickness of the surface, I can imagine that as a very small change in the radius amount, right? So if I have a radius to start that is, I guess, 25 meters long, a diameter of 50 gives us a radius of 25, then painting 0.05 centimeters along the entire surface basically increases the dimension of the sphere radially by that small amount. Just imagine, getting that paint applied everywhere. You've basically created another hemisphere that has a longer radius. It's got radius 25 plus 0.05 centimeters at that point. So I imagine, I'm going to draw this exaggerated, but I just want to get the point across. You start with a smaller hemisphere, and after the painting, you get a larger hemisphere. And the radius is growing from 25 meters to 25 meters plus 0.05 centimeters. I'll have to convert those units. And I'm wondering, what is the volume change? The volume change is going to be exactly the amount of paint that I use, right? Because that is what's occupying the new volume in the bigger hemisphere. Okay, so now I can come back to this equation and see how differentials gets that for me eventually. So the amount of paint I understand to be the difference in the volume of the big hemisphere minus the volume of the small hemisphere, in other words, delta V. That is approximated by dV, the differential, and that's going to be the derivative here. So let me go ahead and take V prime with respect to r. So that would be 2 pi r squared. So it would be the derivative evaluated at the original radius, 25, times dr, which I understand to be 0.05 centimeters. So the original radius, 25 meters squared, times dr, dr, which is 0.05 centimeters. Okay, so this right here is basically V prime of A, where the A value is the 25, and this right here is your dr. Okay, so let me just clean up the units a little bit and I'll get my approximation. So let me just put that into, put the centimeters into meters. So I have 2 pi times 25 squared. This would be 0.0 and then 2 more zeros if I want to do meters. And so that is like 1 over 2 with 3 zeros. So I'll put it like that. And then I'll just simplify this. All right, Wolfram alpha tells me that 5 pi over 8 is around 1.96. So I have 1.96-ish meters cubed. And I just want to put that into a volume unit. So apparently that's like 1960 liters. Okay, and there's your answer to the question. All right, so I just want to summarize what... Okay, I just want to summarize the estimation techniques that are presented in this section. When you have a function that is differentiable at an x value, here are the main ideas. The linearization of the function at x equals a is basically the tangent line used as a function in its own right. So we call it L of x, and it's, just knowing how to get the tangent line from the derivative, it just ends up looking like this. And as I've mentioned before, you have to be really careful when you're creating a linearization that you're actually creating a line. Like, this is a number. This is a number, and of course a is a number. So your answer shouldn't have all kinds of crazy functions in for these things. You're writing down the slope of the function at x equals a. That has to be a number right there. Okay, and then what we just talked about was the differential. Let me write down a couple things. The differential of f at x equals a is called d of y, and it is simply the derivative of the function evaluated at a times dx. We also use the expression for the differential in many other contexts outside of just like using the differential for estimation. So we now sort of have this notational thing. The differential of f is just given by dy is f prime of x dx. So we'll see this notation appear in several other places down the road, in particular when we're doing substitutions and integrals. This differential notation is going to be useful. And I mean, it just looks like, you know, our dy dx notation for the derivative rewritten. And in some sense, it really is. That's how the notation came about.